The class will be a little bit shorter today because I was talking to the on-campus students for a while before I got to to include the DE because we want to keep secrets from y'all. Not really. We were talking about stuff that had to do with just on campus, so I didn't want you to get confused about it, and I just okay. So we have been working on these homeworks. Most of you should have finished this by now. You should be getting ready to start working on these, right? Okay. Remember again, if you've got any ones with problems with TTL characteristics with any of them, you think your answer was right, mine was wrong, just tell me, please look at number 1, 2, 5, 7, 12. I know 17 and 20 were bad, and then look at 24. And those are the ones I'll go look at. And I can pretty much figure out what you've done wrong. Okay, these again are a little difficult, but you'll be able to do it. And I've got to get started on fixing those, or they're going to look kind of funny. Notice this, projects are coming up. Projects, to me, are a little bit more than a homework. It takes a little bit longer. It takes a little bit more thinking, and it's open-ended type stuff. So what I mean by open-ended is I say do this. It's more of a design type problem in some cases, and everybody's answer could be a little bit different and still be right. So I call those projects. Anyway, those will be coming up soon, and they will be coming up like right after the fall break. So, Greg, weren't you supposed to say something about this area of the? Weren't you supposed to say something about this area of the? Wasn't it you? No, okay. Yes, it was, but he's not remembering. His memory is worse than mine.
Yes, it is.
We had a deal. Do you remember? You know, I'm putting him on the spot. He doesn't remember.
Oh my God, I don't remember.
He was supposed to go, hey,
Oh yeah,
what,
practice exam.
what's this thing about a practice exam, Steve? What is that all about? Because what you see on the screen is if I switch my role to permitted student, he's supposed to help me out here. Can't believe it. I don't know why it's taken this so long, but permitted student. So you guys look at this and you don't see it. You just see, here's what we're doing a midterm break. Well, I'm hoping to get through all this stuff before midterm so that I can get back to, so we can go on to the new stuff before then. So I have this practice exam out there. This is just an exam I have used in the past, so you get an idea that I do want to kick your butt on this. And then I've got the answers. A lot of times I won't hand out the answers right away because I find what students do is study the answers and not really try to work through the problems. If you do that, I promise you will fail this test. I promise you will. It's not the way to do this test. You've got to work through it as if it was a real test sitting in front of you right then. And then later, you'll want to see how's it looking. What I will probably do is have you show me or give me some indication that you've completed it. I might be able to see online that you've completed it. I think I can. And then and I can also tell how long you took. So if you go in and open it up and close it and then say, hey, I completed it, can I see the answers? I'll look in there and I'll say, he completed it in 2 minutes. I couldn't write it up in 2 minutes. So no, but I think this time what I might do is give you the answers after you have completed it. Okay, so you can now you guys here you can show it to me. You can say, look, this is what I've done. Okay, it's a great way for you guys to ask questions for the distance students. For you guys to ask questions by typing in an email and say, could you show me how you worked on problem such and such, and I can pull that up and maybe have it ready to go beforehand. Okay. All right, let's pull up where we left off the other day. In fact, the other day, we only went a few slides in, didn't we? So let's just start over. And so we still, looks like kind of a short class, 45 minutes or so. These are the objectives. These are our K-maps. This one, we say binary min terms. We're saying here that A is 0 in this column, and A is a 1 in this column, and B is 0 in this column, and B is a 1 in this column. I said column. B is 0 in this row, B is a 1 in this row. I'm sorry, columns go up and down, right? So here, if you look at that, if both A and B are 0, then the binary result, or not decimal result, is either one, is 0. Here, if A is 1 and B is 0, now we're assuming something here. What are we assuming? Let's look at it this way. Let's go down and look at that. Here we're saying A is 0 and B is 1. So what are we assuming? When we say that this is a 1, that this is cell 1, we're assuming A is the most significant digit, aren't we? Okay. So keep that in mind. Somebody else may have written this and said that B was the most significant digit. You can do that. It's just make sure you know what they're doing. So here's A, most significant digit. If it's a 0 and B is a 1, least significant, we got 1. If A is 1 and B is a 0, that makes this 2. And if they're both 1, that makes this 3. Then I told you some people will refer, I have never done this. I mean, sometimes after a while, once you've gotten good at K-maps and you've done billions of them, you can look at it and you might not think in your mind, this is the domain of A. I don't think I've ever thought in those terms before. But I would look at that. Anything I see there, I know A is a 1. And anything I know in the bottom row, I know B is a 1 there. So I can start picking these up pretty quick. But it is called the domain of A or the domain of B. But that would make this the domain of not A, and this a domain of not B. Here we've got A is 0, B is 0, C is 0, so this cell is 0. We got 0, 0, okay, let's keep it this way, 0, 0, and a 1, so C is the least significant digit because that one's a 1. And then 0, 1, 0 gives us 2 and 3 and 4. Notice we have to skip a step. That's real important. It's the one place I see a lot of students, they mess up once or twice and then they remember. But in moving from one cell to the next, and we can only move horizontally or vertically, no diagonal. So horizontal or vertical. Only one thing can change at a time. So 0, 0. And when we go this way, all these C is 0, so C is never changing. Going from this cell to this cell, only B changed. Going from this cell to this cell, only A changed. And going from this cell to this cell, only B changed. And that gives us 0, 1, 2, 3, 4, 5, 6, 7. These four are the domain of A. The middle two columns are the domain of B, and the lower row is the domain of C. Here, we've got Wait, I don't know where. How am I? Okay, sorry about that. Here we go. Here's a binary minterms for the Carnot maps with AB. So here, I know right through here in the middle, D is a 1. I know the last two rows, C is a 1. These 8 on the right are when A is a 1, and these 8 in the middle are when B is a 1. That's just because I've been doing them a lot. So here it shows the numbers 0, 1. We skip, go 2, 3. 4, 5, 6, 7. The easiest thing to do instead of messing that up is to write these out and then using these binary numbers see that this is 3, that this was a 2, this is 3, and then, I'm sorry, this is a 1, this is a 3, and that's a 2. So we skip this row when we're counting up, and we skip this column when we're writing or counting up. Making 15 almost in the middle, not right down here in the right corner. Yeah.
Are you ever going to make us do like the specifically decimal Carnot maps, or does it matter?
The question is, am I going to make you do it in a specific way? I guess, and no, it's whatever. I don't think I do. Whatever. It's usually whatever. I might say use a Carnot map, and then let you do it the way you're comfortable with it. Sometimes I won't even do that. I'll say find your answer, and I don't care if you use Boolean or Carnot maps. But you do have to know both. So there will be times where I'll say use a Carnot or use a Boolean. And then here's the domains again. Okay, I think that's about where we left off. Now here are the rules to produce that simplest possible expression. In other words, it's how do we put the ones and the zeros from either an expression or a truth table, how do we put them, or once we've put them into the map, we got to go through that too. But once we've put them into the map, how do we pull out the simplest possible sum of products expression? Okay, so here are the rules for pulling out that minimum SOP expression, and that's the way I write it in all the homework types or even on the test. Give me the minimum SOP. And a lot of people in the past have started saying, what is a minimum SOP? Like, well, now you know. Okay, so you first go through this and look around and make sure that you combined the largest group first. Now I've got in there 2 to the n group. So that means you can have a group of 0, that's 2 to the 0. I'm sorry. You can have a group of 1, that's 2 to the 0. You can have a group of 2, that's 2 to the 1. You can have a group of 4. You cannot have a group of 3. Okay? So you can have a group of 4. If you have, let me go back to this, and let's say you had these 3, you can't combine these 3. You got to combine these 2 by themselves and then these 2 by themselves. You'll have 2 groups. But if you had this one, this one, this one, and this one, then you could group these. Okay? So you find the biggest group that is 2 to the n. So what are the 2 to the n's? The largest we're going to get to is going to be a 4 by 4 matrix here, a 4 by 4 map. So we've got 1 by itself, 2 of them together, 4 of them together, 8 of them together, or the whole thing. Okay? If the whole map is a 1, what's the result? It just means they're always 1. No matter what the inputs are, the outputs are always 1. So just connect, forget the circuit altogether, and just put a 5-volt signal there. Okay, Then you keep getting progressively smaller and smaller groups until you're down and you've covered all the ones. Okay? Now we're going to get to a place later in the semester where we're working with some flip-flops. And if you remember flip-flops, how many of you remember them very well? That's about how many I thought remembered them very well. That was no one. Flip-flops have some states where, like, let's say a JK. J has to be a 1. Let's say to set it. J has to be a 1. Doesn't matter what K is, does it? Because if K was a 0, that's the set state. If J was a 1 and K was a 1, that means it toggled to a 1. So no matter what, if J is a 1, you go, or the output is a 1 on that JK flip-flop. So that means K doesn't matter. So we're going to have in some of our Karnaugh maps, we're going to have a star. Some people put a dash. I've seen all kinds of stuff. I usually put a star in there, and that means it doesn't care. We don't care what this particular one is. And you can put a don't care as part of a group if it simplifies it. And you cannot put it as part of a group if it makes it harder. So let's say here again we had a 1, a 1, a 1, and this one was a don't care. Well, that helps, because then I can group these 4. Without it, I've got these 2 and these 2. That's not simplifying it, okay? But let's say these are all that we've got in this whole thing, this 1, 1, 1, a bunch of zeros, a don't care, don't care, don't care. I wouldn't combine these 2 don't cares into anything. Why? You know, it just starts making it more complicated. So you want to use the don't care states for when they're helping you simplify it, not when they're making it harder. Okay. Any redundant groupings should be removed. You don't need to do it twice. Just do it once. Okay, so here we're going to place this expression. First of all, that's what we're going to do, is place that expression into the map. The first one's part of the expression, AB, says, yeah, what am I doing? I'm hurting. My legs and back are hurting from standing up, and I'm not sitting down. Now I am. If I fall asleep, class is dismissed. Because my voice is soothing. It puts you to sleep, right?
You have a lot of trouble.
What?
Your own voice puts you to sleep.
No. It does not. I can talk to my granddaughter, it puts her to sleep. If I talk to my wife, it puts her to sleep. And I don't know what it does to my kids, but they've never heard anything I've said to them. So anyway, here, this is A and B. So if A, and there's no bars across them, so it's not A and not B. It's just A and B. So we're trying to say then A is a 1 and B is a 1, and that's right here where A is a 1 and B is a 1. Right there. Here, and then it says or A. Well, A is a 1 in both of these cells, right? So then to remove this, and see here we've got redundant. We don't need both these ones in here. And since 1 or 1 and 1, whatever, it doesn't matter. They're both 1, it's redundant. Get rid of it. And so we're left over with 2 1s, and they're a group. It's the biggest group we could get. And that means this thing reduces to just A. But look at this. If we were using Boolean, we would factor out that A, have B. Now, some people go, "Oh, you got to use one of those weird rules." No, you don't. You factor out an A, and you're left with B or 1. Well, what's B or 1? That's always going to be a 1. So that A then left with A and 1. A is always going to be the answer there. So this reduces to A. It works easily with K-maps or Boolean. Okay. Trying to see anything. Most of this is
What's the exclamation point?
pretty.
That are not.
Okay, yeah, that's supposed to be a not be. I don't know what a lot of that is up there. A not be. This is the way it is written in some, like in some of the manuals that are out there. They would use this. We had to use that a long time ago when we had just basic text type teletypes or whatever. You couldn't put a bar over anything, so you had to give it some way. Some people would put a slash, some would put an exclamation point, and some would follow this by a single quote. But that means not be here. But you have to know that language or whatever that form is, because you don't know, does this exclamation point go with A or does it go to B? Is this A not and B, or is it A and not B? In this case, it's A and not B. I can see that here. The expression, the binary summation expression, is you look at which ones had ones in their cells. So we have a 1 in this cell and a 1 in this cell. If you remember going back and counting, this is 0, 1, 2, 3, right? So we've got 2 and a 3, and that other 3 that came in there that was redundant, and we can get rid of it and just reduce it to 2, 3, or we can put it in decimal. So if I ask you to enter an expression from a K-map in summation form, that's what I'm telling you. Now, and most of the time in these little homeworks in Moodle, I tell you to just give me the numbers, like 10, 11, or 2, 3. There's still many ways people could turn this in. So what I usually get is some people saying F equals, and they put in a capital E, parentheses 2, 3. Okay, and close parentheses. So I could put the answer in that that's it. But then the next guy would come along and put in F equals capital E, parentheses 2, space 3, close the parentheses. And I have to put that in. The next guy would come along and say, I don't need F equals. So they would just put capital E, parentheses. You can see the predicament I get into. I can't possibly put in every one of these answers. But I do try to simplify it a little bit by saying, please put these in ascending order. So don't have 3, 2 there. Have 2, 3. Okay, if you got 1, 4, 3, and 7, put 1, 3, 4, 7. Okay, so that they're in ascending order. And what I usually ask for in there is just 2, 3. And I do try, I don't always make it, but I'll put in 2, 3, and then 2, space 3. And I try to have both of those as the best possible answer. Now, this is going to be a lot of those where you've typed in the correct answer, but I've marked, or Moodle has marked you wrong. So you tell me, look at this question, or this is one I want you to check. I'll check it. I don't need an explanation. Okay, here's the truth table for AB. This is another way to solve something. for this particular expression, this is a little ridiculous, but it's a good one to learn on. So we've got the the values for A and B. These are all the possible values for A and B. This term A and B, if they're both 0, that term is 0. If 0 and 1, the answer is 0. If it's 1, 0, we get a 0. And if they're both 1, we finally get a 1. And then we've got this column, which is just A. So we can put this column here and say, well, let's look at and put in the values here that are either from here or A. So A, B, or A, they're both 0s. A, B, or A, they're both 0s. A, B, or 1, we got a 1. And A, B, or 1, we got a 1. So this is the truth table for that. But that's what we've already gotten. So I've just, I'm beating this one to death. But it'd be better to beat it to death with these smaller, simpler ones so that you can get to later ones you can get to doing this. Okay. Basically, same stuff. Somewhere, I forget where it is, but there was somewhere in one of the things we have in here where you look at the expression, you just look at it. I know that thing could be simplified. I know it can. But you can't figure out how to do it in Boolean. It's not working out good for you in Karnaugh maps. And you're going, what the hell? Why is this not simplifying? Try simplifying it with the truth table like this. And you can find typically a way to simplify it here, if no other place. Okay. Where are we at? Okay. We're all looking at, these are all the same thing. They're just looking in different ways, right? The binary, the cells with numbers, or the domains. You can use whichever one you really like. Doesn't matter to me. The problem, and the other thing you can do that a lot of people really don't like, and I can't do it here unless I draw it first, but it doesn't matter where you start here. It doesn't matter where you start here. So we could start here with A and B as 1. And then we move to the right, and that means that A is 1 and B is 0. And then we move to the right again, and we get what? It have to be 0, 0. And move to the right again, and we'd get 0, 1. So because, and I know we can do that because on these Karnaugh maps, this cell is next to this cell, isn't it? If I had a 1 here and a 1 here, I could circle them, put them together, and make one grouping. If this cell, this cell, this cell, and this cell, the 4 corners, all had a 1, they can be grouped. Okay, so when we start saying this row is adjacent to this row, then that means I can take this whole row and move it down here. And if this row or column is adjacent to this column, if I wanted to, I could take this column and move this column from here over here. Now, why would you want to do that? You probably wouldn't want to do that. That's fine. I could also have AB over here, where there are the rows, and CD is the columns. I've seen this and another student I had a long time ago used to get in arguments about his book never had it like this. Well, the book I had always had it like this. So that's how I learned. He didn't. He used to tell me you couldn't get the right answer doing that. You can. So I don't know how many times I did it, but it got to the point in that class where every one I did that was through variable, I had to do it his way and my way, just to show him it works either way. But he would have 4 rows and 2 columns, and A and B would be on the side and C would be on the top. That's fine. There's nothing wrong with that. It works. Use whichever one you're comfortable with. It doesn't matter. Okay. Here, I want to reduce this expression. Okay. Damn, I better pick up the speed. There's 98 slides here, and I'm only on 19. Okay, so we put them in like this, then we do this, and we do this, and we do this, and then we say, there it is. No, I'm sorry. Sorry. I'm not going to do that.
I would have walked out.
Yeah, what?
I would have walked out. That's how you're trying to explain.
That would be mean. I've had teachers that would do that. Okay, so we take A and B. Here's the domain where both A and B are 1, right? This is where they overlap. A and B are both 1s. B naught C. Well, here's where those domains overlap. B naught is here, and C is here. So they overlap here and here. Then we got this one. Now it's got 3 variables, so how many 1s are we going to have? The more variables we have, the less 1s we have. The less variables, the more 1s we have. Okay, so here we've got A is 1. That's okay. All these A are 1. Here, B naught is a 1. Well, these 2 and these 2, B naught is a 1. So now we're down to this actual column. And then C has to be a 1, so we're down here. And that's redundant, so we don't even need it. And then we go to the next one, which is A not B, or I'm sorry, A naught, and then B and C. And this is domain of A naught. This is B, so here they overlap, and then we get C. So now we've got to decide how our group's going to be formed. Well, I only see 2 groups there. That group, okay, that's the largest, that should be done first. And then that group. So those are our 2 groups. We got all the 1s combined. And then we take those expressions out of there. This one's C, and this one is A and B. So it should be A and B or C. Okay? Questions? Everything's so simple, right? So I can move on. There's trying to prove this one using the truth table. I'm not going to go through all this. Okay, but this does you use a truth table to get to this place, and then we look and we can see that actually you'd almost have to start figuring out what do you think this is going to be to get that. Okay, but those 2 have to be the same for it to be this to be the same as that one. Okay, reduce this expression. We've got 4 of them now. I do want to get into some good stuff today if I can. A, that's these 8, and B naught, which is this column and this column, so B naught, and then D. D is center 2. Next one is BC. We only got 2 variables, so we got more 1s. If we only had 1 variable, we would have 8 1s out there. What if I said A? Well, then every one of these would have a 1 in it, right? So when we got 4 variables, we'll see that goes down to just 1 1. So B and C naught, these 4 are B, actually these 8 are B, and then these 2 rows at the top are C naught. So that's where they combine. And then A let's see, A is these two columns. B naught is this column, so now we're down to this column. C are these two lower ones, so we're these two now. And then D naught, well, that would be right here. So we put that one in there. And then for this one, we've got the domain of A, and then we got C naught in there, so we got to look at where does all these A's and these two C's cross. That's just these four. And then we got to look at the D naughts, and the D naughts are right here. So we got a 1 there. And that's the that's the simplest combination I could come up with. Could you come up with something different and have it still be the simplest expression?
What do you mean by different?
The simplest sum of products expression is the one that has the least number of variables and the least number of gates. Okay, it doesn't mean it's the best answer. We're going to see that later. But by the simplest, we've taken this and we've reduced it to a real simple A and B naught, or B and C naught. So think in the lab, if you were in the lab and you were connecting this, and this gives you the same thing, wouldn't you rather use this AND gate and this AND gate and then this OR gate? And let's say we had access to A and A naught, B and B naught, C and C naught. So we'd have two AND gates and an OR gate. Here we would have one 3-input AND gate, a 2-input AND gate, a 4-input AND gate, and a 3-input AND gate. And that would be a 1, 2, 3, 4-input OR gate. And you may not have some of those, so then I don't think there is a 4-input OR gate. So you might use a 4-input NOR gate, that's possible, and then an inverter on the end. Or you would OR these two together, and then OR these two together, and then OR those two groups together. It's a lot of working around here. Okay, I want to look at this one first, and this happens a lot. Not this obvious, but this does happen. What if this, 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 and this were also ones? Okay. Now, we have don't cares that we can circle them or put them in the group or not put them in the group. But you must include all ones. And notice I'm doing it. Has anybody picked on something that I don't do that almost everybody else does? Say what? I don't put in the zeros. It just gets in my way. Okay. So if we had these four as ones, what do you think the simplest sum of products would be? The simplest sum of products expression. If we had a 1, a 1, a 1, and a 1, and all these were still there. So there were 12 ones. These are zeros. What would the expression be, though? Okay, let me put it this way. If we circled all or combined all the A's and then had this column, which was A naught and B, so if we had A naught and B or A, would that work? Yeah. If we had decided to circle all the B's, combine all of them, and keep this one, we'd have A, not B, or B. That works too, doesn't it? There's no rule that says we can't overlap these. So we could say A or B because we can't overlap the groups. Now remember a couple classes ago when I said we had A, not B, that's here, and B. So just picture that in your mind for a minute since I don't have it all on the slides. A, not B, or B. That simplifies to A or B. Okay, so even though that may not seem like it simplifies, it does. That's one of the ones that's very hard to catch if you're working Boolean. Okay, if you're just working Boolean, that's a very difficult one to catch. If you had, like we had a minute ago, A here, and this was A not and B. Well, that's the same kind of thing. We've got A or A not and B. That can be AB. Okay? And that's one way, by the way, to prove that would work. So interesting. I like messing with K-maps. The more you use these, the more not only the better you get with K-maps, but the more you see about Boolean operations. You can just see it on there. It's like, well, that's obvious that you got this, and this. But you got to work at it like that for a while. Okay, here's the JK flip-flop. This is one way. There are so many ways to come up with a JK flip-flop. It's not really a truth table, although some people will call it that. This guy I knew used to call them excitation tables. So when we first come here as faculty, before we get tenured, do you guys know what tenure is? It means I don't have to do a damn thing and there's nothing they can do about it. I can do nothing. Actually, that's not true. They could fire me eventually, but it would take a while. And that's not nice to do. I wouldn't do that, you know. But they get you working, and you have so many years to prove that you can do this job. And then they say, okay, not only has he proven that he can do the job, but we believe he's going to continue to do that job. And there are several areas that they test you on or they look at. How many papers have you written and how many citations from those papers? How much money have you brought in for research? How many classes have you taught and developed, and how many of those have you? How many times have you taught them? How many students have you taught? What are your student surveys? You know, how do they come out? The students think you do a good job or not? And there should be at least, how many committees do you serve on in the department, the college, and the community and stuff like that. So there's a lot of things that they look at. I put excitation in there. I probably would have put truth table, but one of the things they do is the tenured professors come by every once in a while and get in a group and they watch non-tenured professors teach. And decide, you know, they fill out this rubric whether we're any good or not. So the guy that taught digital before me always had excitation tables. So by golly, I had excitation tables in there when this came up. The other thing is none of them like me to just use PowerPoints. And unfortunately for my on-campus class, typically I don't just stick to the PowerPoint. I go here and to the board. I do all kinds of things. And I have some teachers that say you should never use PowerPoint and it puts people to sleep. My soft and soothing voice and these boring slides put you to sleep, right? Think if these were black slides and I had the lights turned out, you guys would all be out. Okay, I know it's time to go, but let me tell you a couple things about this just real quick. This is saying the current state of the output, Q, if it's 0 or 1 or 1. Here's our two inputs, J and K. This Q at T plus 1 is the next state. So if this is the current state of the output and the inputs change to J, and I don't care what K is, the next state will still be 0. It won't change. So sometimes they call this the don't change state. If J is 1, the input was 0, or I'm sorry, the output was 0, J is 1, and we don't care about K, then we get a 1 at the output. This is set state. When K is a 1, doesn't matter what J is, it's the reset state. And if K is 0, it doesn't matter what J is. We get 1 on the output. That's the reset state. I'm sorry. This one is, if this were a 1, it's a toggle. It goes from 1 to 0, so it toggles. So if you look at this table, when we're trying to put stuff about JK table or JKs into a K-map, we have a lot of places where we could have don't cares. Okay? And we're going to see those like in some of these. All right? So we'll pick up from them there. What's today? Thursday? Okay, we'll pick up there on Tuesday. Somebody remember which slide I was on? 38 out of 98. Can anybody remember that? And distance ed students, remember to email me with any questions you got. And what I'll try to do is address those in class. And I'll try to, if you give them to me early enough, I'll try to come up with something on a PowerPoint slide or a Word document that I can not only send out, but I could go over in class as well. So send your questions to me, and I'll do my best to answer them in class. Have a great weekend.